Can AI help find the next breakthrough material? One of my side quests on this long world trip has been chasing the answer to this question. AI accelerated materials discovery is fascinating to me because the right material at the right time can revolutionize economy and society. Think steel and the Industrial Revolution, or lithium cobalt oxide, a key cathode for today's modern lithium-ion batteries, and how that enabled today's tech gadgets and EVs. Yet the process of material discovery has little changed from the 20th century, sweaty, repetitive trial and error, or dumb serendipity. In a prior video, I mentioned periodic labs, which raised $200 million from A16Z at $1 billion valuation. But they are not alone in the space. In the United States, we have Orbital Materials and Radical AI, as well as Dunya Innovations and Rara Factory in Europe. I know there might be 2 or so more I haven't heard of. Not to mention DeepMind and Google doing work here as well. Are all of these guys chasing ghosts? Over the past few months, I've read some things and spoke to some people. In today's video, some scattered thoughts on AI accelerated material discovery. Is it real? The first and foremost thing about materials discovery is the sheer unfathomable size of the search space. The periodic table has 118 elements. We can winnow it down by excluding the very rare, expensive, and toxic elements, but that still leaves us with about 60 left to cover. So we combine these elements together and see if it is stable. Then after that, we want to test it for what we call emergent properties. Properties that the individual elements do not have, but their combinations do. A good example of this are the iron nitride magnets. First discovered in the 1950s, these are being investigated as rare earth-free alternatives to traditional magnets. 2 very ordinary elements, but when put together, give you what might be one of the most magnetic things yet discovered. You might need to combine more than just 2 or even 3 elements. Most materials used in practical engineering, steels, metal alloys, glass, etc., have 5 or more elements, some cases as many as 10. The math quickly starts getting out of hand. How many combinations can you make with 5 elements selected from a pool of 60? That is 5,461,512 combinations just by unique element selection alone. And we haven't even mentioned operating conditions yet. At least with drug discovery, we know that the drug has to be effective in the human body's ranges of temperature, salinity, and such. An antibiotic that only works at 500 degrees Kelvin is kind of useless. But materials run the gamut, and that only expands the canvas yet further. And if we want to be complete, then we must also consider crystal structure. There are many ways to arrange the atoms and molecules of a crystal, and varying arrangements can yield materials with entirely different physical properties. An example of it are aragonite and calcite. Both are literally just pure calcium carbonate, arranged in different ways. Yet that is enough for the 2 materials to have different melting points, densities, hardness ratings, or solubilities. This has real-world impact. Previously, I did a little video where an HIV drug couldn't be made into pills because a new, more dominant polymorph suddenly appeared out of the blue. And going back to the iron nitride magnets, one reason why these haven't yet taken over is that their magnetism comes from a unique, difficult-to-achieve crystal structure. This is why it took nearly 40 years for people to acknowledge that these can be powerful permanent magnets. It also makes their synthesis difficult, especially in different shapes and at high volume, as well as to have them maintain their magnetism under heated conditions. The sheer gargantuanness of the search space means that modern material breakthroughs have largely happened via serendipity. Sometimes a known material is subjected to extreme or unusual processing, and then voila, it ends up creating something new and unusual. Teflon is a good example of this. It was discovered in 1938 when Roy Plunkett of DuPont put a large amount of tetrafluoroethylene TFE gas into a metal cylinder for storage. Over time, the TFE reacted with the metal inside the cylinder to form a white inert substance, Teflon. But it seems like the vast majority of breakthroughs occur when someone tests a chemical composition often originally synthesized for something else a long time ago, and accidentally finds it to have game-changing properties for their goals. Lithium cobalt oxide, the aforementioned battery cathode material, was first discovered and investigated in the late 1950s for interesting magnetic behavior, but with nothing coming out of it. It then sat for years before its true calling was found. Nickel-titanium shape memory alloys are another, discovered totally accidentally in the 1960s when someone at a laboratory management meeting randomly held their pipe lighter to a bent piece of alloy and saw it spring back to its original shape. Serendipity is cool, but we can't just spend our lives waiting around to find the next breakthrough material that can vastly accelerate world progress. So a major reason why there's been so much interest in AI is that traditional computational methods do exist for simulating the properties of materials inside a computer. Chemists call these methods first principles, or ab initio, which means from the beginning. It means to solve a compound's fundamental quantum equation, the Schrödinger's equation. Metaphorically speaking, the equation is like an instruction manual that tells you how a quantum system will evolve over time. When done right, you can predict that compound's real-world traits, knowing only physical constants and the compound's electron structure. Such traits include the compound's crystal structures, lattice constants, band gaps, and even optical properties, all without having to actually synthesize the material. The big issue with Schrödinger's equation, however, is that doing it with precision for large quantum systems is beyond the capabilities of even the most advanced supercomputers, and that is because of the many-body problem. Per the Pauli exclusion principle, electrons must interact with each other, with each electron's movement tightly correlated to all the others. So much so that even just adding a few electrons starts to create this wall of complexity that gets increasingly harder to climb. Right now, the fastest computers can run precise calculations for quantum systems of just up to 11 electrons. Considering that systems in practical chemistry might have hundreds of electrons, this is still far short, and without a working quantum computer with millions of qubits, it will remain as such. But approximations do exist for shortcutting the calculations, the most significant of which is the Nobel-winning model density functional theory, or DFT. Invented in the 1960s and refined over the years by individuals like Walter Kohn and Liu Zhu-Sham, DFT simplifies the quantum equation by just focusing on the probability of finding an electron in a certain location. It is now a cornerstone of what we call computational chemistry. Yet even this simplified theory requires a boatload of compute that scales up as the molecules get bigger and if you want more accuracy out of them. And that is despite NVIDIA releasing a few GPU-oriented libraries to help speed things up. Alchemy in particular caught my eye. Helps with some use cases, but not all of them. So now you can sort of see AI's role here. If ab initio models like DFT can indeed calculate a material's property inside a computer, but the issue is that it takes the computer so long to do that, can AI help shortcut those? A metaphor might be like chess computers. DFT methods are like the 1997 chess computer Deep Blue, using brute force computation. Then maybe there is a computational chemistry approach that works more like AlphaGo, AI-centered with less brute force compute. So we deploy DFT and similar theorems to build up a big synthetic training dataset of materials and their properties, like their calculated thermal conductivities or magnetic properties. For additional data, we can leverage existing open-source materials databases like the A-Flow database, the Materials Project, or the Inorganic Crystal Structure database. Once trained, you can imagine the model one-shotting a compound's properties without actually needing to run the DFT. Or better yet, we can set a target for certain properties and have the model spit out candidate materials that it determines can meet those criteria. I think the guys at Google DeepMind are thinking something along those lines. In November 2023, DeepMind published a paper in Nature detailing their new AI tool, GNOME. The AI model predicts the stability of a chemical compound based on its chemical formula, which is then verified or not with a DFT calculation. That data is then fed back into the model. Doing it this way, the AI tool discovered, quote unquote, some 2.2 million stable crystal structures, 736 of which have been independently created before and documented before. By the way, note that GNOME is not a large language model. It's a specialized type of AI model, a graph neural network. Most of the people I spoke to agreed that the models for AI materials discovery probably won't be the same size as a GPT-5 or even 4. So this is the way, right? Time to synthesize some data. The issue, however, is DFT's central role in this workflow. I want to add here that I hear varying opinions on what follows. Most chemists and material scientists agree that DFT is theoretically sound. It won a Nobel, after all. But in practice, DFT, like any tool, works better in some applications and worse in others. The theory does not seem to work well when there's a lot of complexity, i.e., when the system is particularly large or in high temperatures, or when the crystal structure is complex, like with grain boundaries. And since DFT starts slowing down with larger systems, we end up building a dataset of mostly smaller, simpler molecules. Does small molecule data scale up to big molecules? We aren't sure yet. Here is another concrete example, magnetism. All these AI materials discovery startups talk about magnets, and for good reason. China's grip on the rare earth magnet is strong, and they're wielding it like a hammer. I want to speak rather carefully here because I'm not a magnet expert and I haven't done the reading yet. But what I am told is that DFT is not great at predicting what is called itinerant magnetism, where magnetic behaviors emerge from the structures of certain metal alloys, perhaps because so much depends on the collective behaviors of electrons in those alloys. The pitches of many of these recent startups, especially the American ones, lean heavily on the compute side of the equation. And I am not saying that the compute stuff won't work, but per what I mentioned above, it would be flimsy to lean on only that, not only due to DFT's aforementioned shortcomings, but also because you can't outcompute DeepMind and Google. So it seems to me that the lab side is essential. Data generated synthetically using DFT or other methods, augmented with data produced in real life in special high-throughput labs. All of the AI material startups will have to invest heavily into this. One can draw inspiration from the high-throughput methods practiced in the pharmaceutical industry. There, massive parallelization and automation allow companies to make and screen hundreds of thousands of compounds each week. You need to be able to both synthesize and screen. On the screening side, there are not many metrics that can be screened at scale, but spectroscopy tools do exist that can test optical and electrical properties like bandgap, conductivity, and carrier mobility, and mechanical properties can be tested with a probe. The high-throughput synthesis side is a bit more complex. Some methods do exist: micropipetting done by robotic arms, microfluidics, dip pen lithography, where an atomic-sized probe puts together precursor material molecules, thin film deposition that can lay down combos of precursors onto a plate or silicon wafer. One should note, however, that synthesis quality remains spotty and limited. For instance, high-throughput synthesis methods struggle at producing specific crystal structures at high volume, which is a big deal in determining critical properties. A lot of this is uncharted ground, so these startups will have to make difficult choices and learn difficult lessons. And because we are dealing with the real world, deadlines will be missed. And that is a problem if you're investing. One thing overhanging all this work are the economics. No way around it, the economics of materials discovery suck. They are challenging, especially on a venture capital funded model where you're always rushing to the next round. The economics of materials discovery are like drug discovery without the rich financial gains that pharmaceutical companies enjoy from their drugs' patent protection period. Even after finding a suitable compound, you still have to invest time and money to prove it works, learn how to make it at scale, and secure the supply chain. This can take 10 plus years and tens of millions of dollars. Then in the end, if you somehow win the lottery and figure it all out, someone else enjoys most of the economic gains from this new material, the end user. And they often being a far larger company and the sole client, they can grind you down on licensing price or IP ownership. Side note, it also somewhat concerns me how the startups all seem to be going after the same markets: magnets, thermal/electrical conductors, new battery chemistries, and maybe superconductors. Yes, they are the most high-profile markets, but something about that just bothers me. Before we conclude, I want to say that this analysis remains ongoing, and if I've said anything that does not ring true to you and you work in the industry, I invite you to do a video call with me. Educate me. I have been so interested in this because I feel like the discovery of new materials will be crucial for technological progress, and that computers, and AI in particular, can help. I do think it's a great thing that the VCs are funding materials research. Materials funding has declined in general since the 1980s. Yet at the same time, for those who want to go out there and discover new breakthrough materials, the challenges are daunting. It means coordinating efforts in both software and hardware, while also educating investors that the returns won't be like consumer software. It is definitely possible that one of these startups finds and commercializes a new breakthrough material. That will make me so happy. Those who do not, I think, will end up pivoting to building new tools and platforms to sell to internal R&D labs at industrial companies. Or perhaps agentic AI approaches that theorize and experiment and learn like material scientists do. Maybe. Such tools can be just as big of a deal because it helps unlock new gains at these companies and accelerate their productivity. The space is very early, but I look forward to seeing what they can find. All right, everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.